The goal of the project in this video is to do single-channel based interpolation. Interpolation is really important for when you're measuring some system with a lot of sensors, let's say an array of pixels in a camera, and you have a couple of corrupt pixels, a couple of corrupt sensors. Then what we're going to do here is use scattered interpolant to interpolate those missing data values. Let me first show you what this looks like. So here I have our original data. This is actually exactly the same data that we generated in a previous video on simulating tri-component time-space data. And the first thing you're going to do in this project is to corrupt the data by coming up with some proportion of pixels. I think this is 10%. So 10% of the pixels are corrupt and they have high amplitude noise. And now we're going to work with this data set. We will need to come up with a way to identify these bad or corrupted pixels. And then we are going to use the scattered interpolant function to interpolate the data at these pixels, each of these noisy pixels, and that will give us this. So this is the final result. This is the original image, and this is the corrupted data that we're going to interpolate in order to get this image. So that's the main assignment. First, you want to corrupt random pixels. Then you want to interpolate those pixels using the MATLAB scattered interpolant function. The bonus exercise is to use the set function to generate a movie of all of these data sets. So now I'll switch to MATLAB and I'll show you how I solved this problem. Here's a reminder that the data that we're going to use in this project is called multi-data. This is literally the data that we generated in a previous video, a previous project, to generate multivariate time-space data. It was called tri-component space data. I'm not going to regenerate the data here just because it will take up more time, and that's why I had that entire dedicated video. So here we figure out the proportion of corrupted channels or pixels, and I'm going to set this to 0.1, which means 10%. Now what we want to do is pick 10% of these sensors or pixels randomly to be replaced with noise. So how are we going to do this? Looking down to this line, you can see this says bad sensors from 1 to the proportion correct times n squared. Well, n squared is the number of total pixels in the image because the data set is 50 by 50. So what does it make sense to get from 1 to 10% of the image? Well, what we want to do is shuffle all of the ordering of the pixels, so that will give us a random sampling of pixels. So this is something I've done before in previous videos to select random time points. So we do rand perm, and we want n squared random numbers. And that's going to give us this set of random numbers, 250 random numbers. And these are the pixels that we will replace with large amplitude noise. So now we're going to loop through time. This is going to be the original data set. We don't want to touch this. So I'm going to generate a new data set as a copy of the original data set. And that's going to be called multi-data C, where C is for corrupted. So first I loop over time. I'm going to get the matrix corresponding to just this time frame. So this is going to be the tith element. So this will be a 2D matrix. Let's run this. Here's a 2D matrix. And now I want to replace the bad sensors, which is in this variable, with large amplitude noise. Notice that this matrix temp is a 50 by 50 matrix, but this variable, bad sensors, is a vector. It's 250 points long. So that means we're using linear indexing to go into this matrix. So I'm going to replace these by some random values. So say rand n, and it's going to be the length of bad sensors. Oops, bad sensors by 1. But I want to make sure that these are really large amplitude noise spikes relative to the existing data. So I'm going to multiply this by some large number, let's say 100. So this just replaces the data in this little matrix temp, and then we need to put that data back into this data set. So now I'm going to say multi-data C, and it's this time point, and all of these space pixels equals temp. So let's run this code, see if we get any errors. Okay, no errors, that's already the first good sign. And now we want to visualize this data set to make sure that it did what we expected it to do. So I'm going to open up a new figure, and here we set up the figure. So it's going to be 3 subpanels. Initially, we're only actually drawing 2 things, but we're going to add the 3rd subpanel later when we do the interpolation. So here is image scale, and this is going to be in a movie where I'm going to update the color data of this image. So for now, I just need something. It can be the average, it can be all zeros, it can be random numbers. As long as it's the correct size, as long as it's 50 by 50, anything will be fine in here. So then I set the color axis, make it square, and give it a useful title. So let's run this. So here's the handle to the original object, not to be confused with O. Here's the handle to the corrupted image. And now I want to update the display. So we loop over time points. And what do we need to do in here? Well, we need to set the original handle. And what's the property that we're going to set here? It's the color data. And what do we set the new color data to? That's going to be squeeze multi-data. And now this is the original image. So I'm not using the C matrix, just the original matrix. And it's this time point, all of the pixels. Okay, so now I want to run this for the first time point, just to make sure that this line of code is accurate. Yep, so it didn't give an error, and it updated the plot here. And then the other thing we need to update is the CH, the corrupted image handle, and that needs to be multi-data C. Great, so let's run this video, see what it looks like. Brilliant, here you see all the corrupted pixels. They're a bit sparkly, and it looks really awful. All right, so when you look at this image, when you watch this video, it's painfully obvious to you which pixels are bad. But how can we write some algorithm? How can we make MATLAB know which pixels are bad? Well, I have an idea. Why don't we start from the assumption that the bad sensors have a very large variance relative to all of the good sensors, or the good pixels. This is obviously a pretty sensible assumption, considering that's exactly how I generated these data. So this method that we're going to use here for identifying these bad pixels is not necessarily a one-size-fits-all solution. In fact, it could be that all these pixels have a very low variance if they were all fixed, if they were pinned to one single value, and that value never changed over time. In that case, these would all have the same value at every time point, and the variance would be small, would be 0. Anyway, but looking for pixels with very high variance is going to be a good solution here. So in a different figure, I want to make an image of the variance map. The variance map is just the standard deviation of the data. And the standard deviation function, I believe we're going to need to squeeze this to make sure it's two-dimensional. The standard deviation function will take 3 optional inputs. The second input is a normalization factor, which we don't care about here. The third input is the dimension over which to compute the standard deviation. Now I think by default it's 1, so we probably don't need to have this input here. But I'm just writing this so you are aware of this feature of the standard deviation function. If time were in the 3rd dimension, for example, we would have to do something like this. The reason why this is a little bit difficult to remember is that if you're thinking of the mean function, in the mean function, the dimension over which to average is the 2nd input. But with the standard deviation function, it's the 3rd input. So go figure. Here we go. So this shows that all of these other pixels, these are all good pixels, they have relatively low variance. And all of these red pixels, these have really, really high variance. So let's make a histogram of all of the standard deviations. And to identify a threshold, I'm going to convert these to a Z transform. So I want to take all of the standard deviations in this image, except I want this to be a vector and not a matrix. So to do that, I'm going to take exactly this same code here, and then I'm going to reshape it, and we're going to reshape this 2D matrix into a 1 by whatever is left over vector. So let's see what that looks like. So it's 1 by 2500, which is n squared. I can plot this. Here you see the variance. These are all the good pixels all the way down here. You can zoom in. These are the variances of the good pixels, and of course the bad pixels have super high variance. This is not z-scored, so I went to z-scored, and the formula you'll remember for z-scoring was to take the vector minus its mean divided by the standard deviation. And here it's really important to have these parentheses in here, otherwise the order of operations will dictate mean divided by standard deviation, and then this quantity subtracted from all of the individual values, which is not what we want. Good, so let's do this and make a histogram. Oh right, yeah, so we're computing temp z here, so this is just temp. Now let's look at the histogram. Great, here we have all of the pixels with small relative variance. Here are all the pixels with large relative variance. Let's say the threshold is going to be 2. Why not? So here I type the sensors to interpolate are basically any pixel which has a z normalized standard deviation greater than 2. And let's see what that is. So now I'm going to plot sensors to interp. This is a Boolean vector because we just do a logical test here, so they're all zeros or ones. And you can't really make a whole lot of sense out of this, but I still think it's important to look at these kinds of plots, because if this were all zeros or if it were all ones, then we would immediately know that something went wrong somewhere in here. Another thing I'm curious to do is take the sum of this to see how many sensors we identified to interpolate. And it ends up being 250, which is no big surprise because that's exactly how many pixels we said should be corrupted up here. This is one big advantage of simulating data. You know exactly what the ground truth is, so you can compare your algorithm. If this algorithm told us that there were, 47 pixels to interpolate, then we would know that something is wrong with our algorithm. We have to change the threshold or something. Great, now let's do the interpolation. So now I'm going to create yet another data set. This is called multi-data R. And I think the R here stands for reconstructed or something. You could also call it I if you want for interpolated, but let's leave it as R for now. Now I'm initializing this just to be zeros. So let's walk through this code step by step. So first we want to loop over time points, little typo there. And so here we are at the first time point. We want to get a 2D frame of the data. So again, I'll call this one frame, and let's set that equal to squeeze multi-data C. We're only working with the corrupted data now from this time point. And then what are we going to do? Then we're going to use this function called scattered interpolant. If you've never heard of this function and you don't know how it works, then don't worry, you can just open up the file or type help scatter interpolant and read a little bit about how this function works. You can go through a few of these examples. I certainly encourage you to pause the video and familiarize yourself with this function a little bit. But for now, I'm just going to tell you how this works. So the way that scattered interpolant works is we specify column vectors of all the x coordinates, all the y coordinates, all of the good data points. So we're only dealing with the good data points, not the bad data points. The output of this scattered interpolant function is going to be a function. It's another function. And then the way we interpolate the missing data is to call this function with the locations, the xy locations of the missing data points. So let's get started. So what are the good data points? Well, the good data points are in X, so this is the matrix X that you generated from the previous code from MeshGrid when generating this original time series, and Y. And the good data are in one frame, this matrix one frame, except this is not exactly what we need. So first of all, these need to be column vectors. like this. But also I said that these have to be only the X and Y locations and data values for the good sensors. And this is for all of these sensors, all the pixels. So what we need to do is use this sensors to interp function, or variable. So this is going to be sensors to interp. Except that actually these are the bad sensors. These are the sensors that we want to interpolate. So how do we get from this vector to the vector of good sensors or good pixels? Well, we can just invert this Boolean vector like this. So now we get a vector with mostly ones and 250 zeros. So that's for the X. And then for the Y, it's going to be the same business, sensors to interp. And for this, the variable one frame, which actually contains the data from this time point, we only want the good sensors. So let's see what happens here. Oops. Now let's see what happens here. Right, so I did mention that these need to be column inputs, and these are currently not as column inputs. So I need to transpose all of these. And now let's see what happens. All right, so it doesn't give any errors, so that's a good start. And now we get this variable f, which tells us a little bit about this function. So these are the valid points. These are going to be the x, y locations. These are the values at those locations. And by default, it does linear interpolation, also linear extrapolation, although we're not doing any extrapolation here, just interpolation. So let's see what these look like. To give you a bit of a better sense of what this function means and what it's going to be doing, what the inputs are, I'm going to take a little bit of an aside, and I'll do it right here in the code. So first I'm going to specify a little variable x, and that's going to be equal to these points, and then a little variable y, and that's going to be equal to these points, and a little variable z, and that's going to be equal to these values. All right, so now let's see what x and y are. I can say plot x by y, and let's make these squares. Oops, like this. So you can see these are all the xy locations of not all the pixels, but these are actually all of the good pixels. Everywhere where there's a little box missing, that's the location of a bad sensor, a bad pixel. And that's going to actually correspond to all of these guys here. And what is Z? Well, Z is a bunch of numbers, and we can use these to define colors. And to do this, the best way is the scatter function. You'll remember the scatter function from the section on 2D plotting in this course. So we're going to plot x by y. Let's make these, I don't know, 50 size. The size corresponds to 50. And then the color will be Z, and let's make them filled. All right, so this is what the dots look like for this frame. So you can actually think of this as three-dimensional coordinates. It's x and y, and then the z is like the height, which is here mapped onto color. Great. And by the way, this way that I wrote out the code and made some plots and scatter plots and explored this, I'm not only doing this right now for your benefit. I'm doing this to try to show you one way to use MATLAB to help you understand what functions do if it's not really clear what they're doing. So I'm just plotting the inputs, and then we're going to plot the outputs as well. Okay, so once you generate this function from scattered interpolant, the next thing to do is apply that function to the missing data. So what I want to input into the function are the xy coordinates of the bad location. So that's actually almost exactly this, except now we actually do want the bad sensors to interpolate. Now I'm not inputting the values because presumably these are crappy values. These are values that I want to replace with a linear interpolation at those points. So let's see what P is. P is 250 points long, and that corresponds to one value per faulty pixel. Okay, so now we have this original variable one frame, and now we want to put that one frame, the interpolated data points back into one frame. So that's pretty simple. I just say like this. And finally, put that frame back into the data set. So that's going to be one frame. So first of all, before I run this, let me just run these codes, and I'm going to make an image of one frame. Here's our bad pixels. And now I replace one frame, the bad pixels with P, and then I'm going to make an image of it again. And now it looks totally different. In fact, let's see what I want to see what the color scale is. So this is around, actually let's do this, subplot. And now I'm going to set this color axis to be -1 to 1. And then in a subplot over here, now I'm going to run this line and then make another image. Oh wait, sorry, I wanted to do the original one. There you go. So on first visual inspection, it might look like these are totally different, but that's actually just because the color scaling is totally different. So now if I set the color scaling here, you can see that these really are the same image, but this one has a lot of really, really large values, and it totally screws up the color scaling. Okay, so I think this loop is complete, so I'm going to run this entire cell, take several seconds, but it didn't give any errors. And now we need to make a final video of all the images. So now I'm going to go back to figure 1. So set up a handle. This is going to be, in fact, I'm even going to copy this from up here. Where was this? Up here. Yeah. So we have the original data, and then I'm going to copy and paste this. So obviously we need to change this image handle, and it looks like it's going to be called handle 2 and handle 3. So I'll call this handle 2. This has to be the measured data. And down here I'm pasting again, and now again I need to change this to 3. And then this is the reconstructed or interpolated data. Now notice here, I'm just going to leave all of these as the original data. That doesn't really matter, because what I really care about is updating the color data in this plot. So if you want, you could set this to be multi-data R and this to be multi-data C, but that's not really important. Right, so this handle is replaced with the squeezed version of multi-data for this time point and all pixels. And, oh, there is already squeeze here. And then copy, paste, copy, paste. This is going to be R, and that's going to be C. All right, so now I'm going to run this whole cell, which basically just does some plotting, and we will see what this movie looks like. Brilliant. This looks really great, really beautiful. All of these dead pixels or faulty pixels are completely removed, and you wouldn't really notice that this used to look like this. Now this works so beautifully here because these pixels are really horrible, and because this original image is sufficiently smooth that this linear interpolation works really well. This is not always going to produce such beautiful results. If you have a lot of high frequency spatial features in this movie data, it might not work quite as well. Nonetheless, it's really useful to know how to do spatial interpolation in this kind of way.